Hello everyone, my name is Raina Dijut and welcome to my Module 7 Concepts video. In this video, we're going to slow down and really dig into three of the most important technical concepts within this project. These concepts show up in a lot of different web apps, so if I understand them here, I'll recognize them everywhere. The three concepts we're going to go over today are JWT authentication and token-based authorization, client-side state management with React hooks, and database schema design and validation. So for each one, we're going to start simple, build up gradually, and then look at real trade-offs and alternatives. By the end, we'll have mental models that we can apply to other concepts. So without further ado, let's get into it. So the first concept is our JWT authentication. The problem that is being presented with this is how do we prove who we are and that we have access to this information. Let's start with the fundamental problem. So imagine you go to a bank and you need to withdraw money. The bank asks, who are you? You can say, I'm Raina Dijut. But that's not enough. Anyone could claim to be Raina, so the teller will ask you for an ID. You show them your driver's license, it's physical proof of who you are, your photo, your signature. It's kind of hard to fake. In a web application, we have a similar problem. The user logs in with a name and a password, the server verifies that they're legitimate, but then what? How does the server know that the user is still legitimate when they make the next request? So there are two traditional approaches. Approach number one is server-side sessions. So after login, the server stores a session on its hard drive, user 123 is logged in, and they are Raina. When the user makes a request, they send a session ID, like a ticket stub. The server looks up that ID in the memory and says, oh, this is Raina, I know them. The pros of sessions is that they're simple to understand, the server has full control and can revoke sessions immediately if necessary, and they can store extra data in the session. The con of the session is the server must remember every logged in user. If you have 1 million users, that's 1 million entries in memory. If you scale to multiple servers, they need to share session data, which adds a lot of complexity. If the server crashes, all the sessions are lost. Approach number two, which is what we used here, is token-based authentication or JWT tokens. So when a user logs in, the server doesn't store anything. Instead, it hands the user a tamper-proof token. The token is like a passport. It says, this is Raina, user 123, valid until tomorrow. The server signs it cryptographically so nobody can forget. On every request, the user sends the token. The server reads it and says, okay, this is Raina. It doesn't need to look anything else up. The pros of tokens is that they are stateless. The server doesn't store anything. They scale easily, so any server can identify the token. They're mobile friendly, so native apps use tokens and not cookies, and they can be revoked by setting a short expiration. The cons are once they're issued, they can't be revoked immediately. If the token is stolen, it's technically valid until expiration. Token size is larger, so it contains more data than a session ID, and it requires careful secret management. The Rocket Elevators app uses JWT tokens, and this is the modern standard. JWT stands for JSON Web Token, so let's look at a real example. So looking at our DevTools on our page, here is the token from our app. It's this really long string of letters, numbers, and characters. And our tokens expire after 24 hours. If a token is stolen, someone reads it from our local storage, it's only valid for 24 hours. After that, the hacker would need to steal a new token. But 24 hours means users have to log in every 24 hours, which is annoying. A better approach for larger apps than what we have would be a refresh token. For the Rocket Elevators app, simple access tokens are probably fine, but in a production app handling sensitive data, refresh tokens are better. Common JWT mistakes. So mistake one is storing JWT in local storage. Local storage is vulnerable to cross-site scripting attacks, so if a malicious script were to run on my page, it can read my local storage. The better approach is to store refresh tokens in HTTP-only cookies. These can't be read by JavaScript, only sent with HTTP requests, so this prevents cross-site scripting attacks from stealing tokens. For access tokens, HTTP-only cookies are fine too, but local storage is acceptable if you trust your dependencies. Mistake number two would be not validating on the back end. A hacker could use browser developer tools to change or delete the token, so we always validate the token server side before processing any request. And mistake number three is hard coding the secret key. We never want to hard code the JWT secret in our source code. The secret has to be in environment variables, so it's not committed to version control. So moving on to our second concept, which is React hooks and state management. The problem that this concept solves is how do components remember things? Let's think about a simple problem. When a user types in a form field, where does that text go? It can't go in a variable because variables are local to a function. In React, component functions run multiple times, so if we store data in a regular variable, it would reset on every render. React needs a way for components to remember state between renders. The solution is hooks. A hook is a special function that lets a component hook into React features. The most important hooks are useState or component memory, which can be seen on our login page.jsx. For instance, this constant email, set email, and useState, this creates a state variable, so React will remember the value even when the component re-renders. So email is our current value, set email is the function to update it, and these quotation marks is the initial value. So when we call set email John add example, React will update the value, re-render the component, and now the component sees the new email that we updated. And side effects are things that happen outside of a component. So API calls, timers, DOM manipulation. UseEffect lets you run them at specific times. So for instance, in our agent list page, we see this useEffect and then fetch agents. And at the bottom here, we see these empty brackets. These empty brackets is the dependency array, so it controls when the effect runs. Let's look at a real example, the agent list component, and let's trace through the flow. So these agents loading and error is the initial render. The component renders with the loading message. After the mount, the useState runs and calls our fetch agents, which can be found here. Then we set loading true, and we set error null. The async fetch starts and returns to our caller. Then when the response arrives, our set agents is called. React re-renders with new agents. It still shows loading because we haven't called the set loading false yet. So once we call set loading false, React re-renders again, now that loading equals false, so the component renders the agent table and the agents. This pattern repeats everywhere in this app. It handles the asynchronous nature of data fetching gracefully. And if you notice at the top these 3 state variables, this is a pattern that occurs all throughout our app. In this app, the parent component, which is our agent list page, fetches the data and manages the state. Child components, like our agent table, receives the data as props. When the user clicks on delete, the child calls on delete, which calls the parent handle delete function. The parent updates the state, re-renders, and the child receives new props. This flow is called lifting state up. State lives in the component that needs it, the parent, and is passed down as props. Why not let each child manage its own state? Because if multiple components need the same data, they start to get out of sync. By putting state in a parent, there's a single source of truth. So that's all I have on concept 2. Let's move on to concept 3, which is database schema and validation. This is a recurring concept for me because it's kind of the same but kind of different depending on which app I'm working on. So I'm going to go over it again for my sake and for yours. So the problem that this concept is solving is garbage in, garbage out. Imagine you're running a company. You store agent information in a database. One day you query for all agents with a rating greater than 80 to give them a bonus. But the results are weird. Some agents have negative salaries, some have ratings of 500, some recorded an agent's name as the number 12345. How did garbage data get into the database? Maybe a bug in the code sent invalid data, a hacker bypassed the API, or someone manually edited the database. The problem is that the database didn't validate the data coming in. It accepted anything. This is why schemas matter. A schema is a contract that says data must look like this. If data does not match, it's rejected. So our app uses Mongoose, which enforces schemas on MongoDB. So let's look at our agent schema, which can be found here in modals. Let's break down each field. So first and last name. The type is the string, required is true, which means it can't be omitted, and then trim is true, which means any white space is removed. And then for region, type is string, just means it must be text. Enum means it must be one of these values that we have already predefined, which enforces that region names are consistent. And then if we look at rating, fee, and sales, the type is number. The default is set, so if somebody does not enter in a value, this is what the default is automatically set to. And there is a minimum of 0, so there can't be any negatives in these fields. So say we were to try to create an agent that had a rating of 150. In the backend handler, Mongoose creates the object, but when save is called, it validates. The validation fails because 150 is greater than 100, which is defined in the schema. So then Mongoose would throw an error. The front end would receive a 400 bad request and can show an error message to the user. So the first layer is our front end validation. This would give instant feedback so the API call never happens if bad data is input. The pro is that it's fast and there's no network round trip and it's a better UX, so there's an immediate error message. The con is that it can be bypassed. A hacker can use curl to skip the front end. Layer 2 is our backend validation. So the backend validates before ever touching the database. This stops bad data before the database ever sees it. And then layer 3 is our database schema validation. So the schema is our last line of defense. Even if bad data somehow gets past the application, our database will reject it. All three layers are important. Front end for the UX and for responsiveness, back end for security because the front end can't be trusted, and then database is our last resort for data integrity. The trade-offs is that SQL databases enforce strict schemas, so every agent must have exactly the specified fields with exactly the specified types. The pros of this is that it enforces consistency across all the rows, prevents accidental bad data, queries are faster, and data integrity is high. But the con is that it's harder to evolve. You can't have some agents that have extra fields, and it requires a lot of upfront planning. MongoDB is a little bit more flexible and allows different documents to have different fields, but Mongoose adds the validation on top. So it's easy to add new fields. You can gradually migrate data. Different documents can have different structures. The cons is that it requires discipline to maintain consistency. Queries can fail silently if fields are missing, and you need to validate in an application code. For Rocket Elevators, MongoDB works well because the agents are simple entities. There's not many relationships. The schema is stable, so we're unlikely to add a bunch of fields, and flexibility lets us iterate quickly. Here's the mental model that I have for schemas. I look at it like a contract. So a schema is a promise. All data in this collection will look like this. It defines what fields exist, what types they are, and what rules they must follow. The database enforces this contract, rejecting data that breaks it. This prevents garbage data from accumulating and keeps the database trustworthy. So, in summary, we have covered three fundamental concepts: JWT authentication, which are stateless tokens that prove identity without server-side sessions. The server signs tokens so they can't be forged, and tokens have expiration limits to limit the damage if they are ever stolen. React hooks are functions that let components remember state between renders. So use state for data, use effect for side effects. The three state patterns, loading, error, and data, handles async operations elegantly. And then database schemas, contracts that enforce data structure and validity. Mongoose validates against the schema, preventing garbage data, and layered validation, front end, back end, and database is the best practice. These concepts work together. So when a user logs in, the front end sends an email and password, the back end validates with user schema, password hashing, JWT token is created, JWT is sent back, and then the front end stores it in local storage. For our get agents, the front end uses use state hooks to manage loading, error, and data. Use effect fetches on the mount. JWT token is sent in the header. The backend then validates the JWT. Agent schema enforces the consistency, and then the data is returned, and set state updates React, and then the component re-renders with the data. Each concept solves a specific problem, and together they build a robust, secure, and maintainable application. So, I hope that made sense. Thank you for watching, and I will see you on the next one.